This video is part of the Commercial Building Electrical Design series. It's in the Power Distribution Design section. We are looking at ways to form branch circuits, and this lecture we're going to look at branch circuits for motor loads. So just a quick look to see where we are in the series. Again, we're under power distribution. We've looked at delivery systems. We've gone through basic materials, and now we're exploring the different types of branch circuits. So again, now that we've reviewed some of the basic materials used for distributing power, we'll now focus our attention on some of the basic elements of power distribution systems. The most basic element in the system, of course, is the branch circuit. So this is a circuit that distributes power to individual loads. In general, the branch circuit is usually derived in a branch circuit panel from a branch circuit breaker. So we'll now examine some of the different types of branch circuits and how these circuits are sized. So we're going to look at motor circuits. So this is the final class of branch circuits that we want to take a look at, and these are circuits that feed motors. Motors are a very different class of load in that they typically require a very high inrush current to start the motor, but once the motor is running in a steady state, the current then drops to a much lower level. So motor circuits are addressed in the National Electrical Code in Article 430. So before we look at the calculations for these types of circuits, I think it's first if we begin with looking at some of the definition of terms that are commonly used in reference to motors. And these are terms and acronyms or abbreviations as well. So the first term we want to look at is full load amps. You'll see this abbreviated as FLA. So this is the amount of current that a motor draws when it is fully loaded and running in a steady state condition. In general, most motors are not designed to operate fully loaded in normal operation, at least not all the time. However, the electrical circuitry feeding a motor must be designed and sized as if it were to be operated under full load. The FLA value can either be obtained from the motor manufacturer or on the motor nameplate, or more commonly it can be attained from the National Electrical Code Table 430.248 or 430.250, and this is based on voltage and horsepower for standard size motors. So this is the primary value used in calculating the breaker and wire size for the motor, so it is very important. And we'll look at these tables a little later in this lecture. So here's table 430.248, and so this is the full load amps for a single phase AC motor. And so if you've got any single phase, they come to this table to look for that, and you see here's the horsepower on the left side. So we pick our horsepower and it goes up to 10 horse. And then we have our corresponding voltages, and that can either be 115, 200, 208, or 230. So it's pretty simple. You do need the horsepower and the voltage is the minimum information we need, and once we have that, we can cross-reference into say like a 3/4 horse motor running at 208 volts would draw 7.6 amps under full load. This is table 430.250. So this one is for 3-phase AC motors. The previous table was for single phase. And so you can see it's got a lot more choices here because the horsepower goes way beyond 10 horse. We go all the way up to 500 horse. And again, we have our voltages, and you'll notice that there's two basic sections of this table. There's an induction type squirrel cage and wound rotor motors, and then there's the synchronous type unity power factor. So in general, we'll almost never be in this column. You don't see these motors very often except for very special circumstances. So when we look at this table, we stay in this section here, the induction type motors. And so again, you just find the horsepower, you come over to the voltage, say it's a 480, 125 horse, that should draw 156 amps under full load. It is worth noting down here, they do have power factor correction, so if you do know that it's running under a lower power factor, you should multiply by these power factor corrections. So you see as the power factor goes down, the full load amps go up, respectively. Another term or abbreviation you're going to see is MCA, which stands for minimum circuit ampacity. So this is the value used to choose the size of wire, or at least the minimum size. A larger size can be used if needed or desired, to feed the motor or motors. This value is obtained for a single motor by simply taking the FLA, which we just talked about on the previous slide, and multiplying it by 125%. And this is from the NEC Article 430.22. So this value is used along with the ampacity table for wire in Article 310 that we looked at before. For a single feeder that will be feeding multiple motors, this value is calculated by taking the largest motor in the group and multiplying it by 125%, and then just adding up the FLAs of the other motors without multiplying by that 125%. So you only have to multiply the largest motor by that and then just add the others together. And this would be the value you'd use to size a single feeder that would eventually be tapped to feed multiple motors. Another term you might see, but it's not as common, is RLA, which stands for either, I've seen it both ways, running load amps or rated load amps. So this is the amount of current that a motor draws when it is running under design load, which, as mentioned above, should be equal to or less than the FLA in most cases. Sometimes this is given in lieu of the full load amps, or sometimes the FLA called by a different name. The FLA should be used if known or can be obtained. Otherwise, this value can be used in substitute or in place of the FLA in calculations for the wire and breaker size. Again, if we don't know the FLA for sure. Another term that you'll hear is locked rotor amps. That'll be abbreviated as LRA. So this is the amount of current that a motor draws when the rotor is locked and not able to move. So if you had something that bound the rotor and it couldn't move, but it was still trying to make it move, it'll continue to draw more and more current up to this maximum amount, which is called the locked rotor amps. So when this happens, it causes a tremendous amount of current draw. This value is typically given on the motor or equipment cut sheets, either the value itself or it'll give you a code. If it's not given, or if for any other reason it's unknown, the designer should allow for at least 4 times the full load amps to compute this value, but in many cases it's even more than that. And so, if we look at a motor, that's if this rotor, this piece here, is locked. So either it's in a bind or whatever it's trying. If it's like trying to stir some type of liquid and the liquid's too thick, the viscosity's too high, it'll lock that and lock the rotor. So another term you'll hear is maximum overcurrent protection. You'll see this abbreviated as MOCP. So this is the maximum size breaker that can be used to feed a given motor based on the full load amps and the size of the motor. The reason that this is a maximum number is that the National Electrical Code actually gives a range for breaker sizes up to 250% for most breakers. We'll look at this table, but it comes from table 430.52 in the National Electrical Code. According to the National Electrical Code, for thermomagnetic breakers feeding a single motor, the maximum breaker size that can be used is 250% times the full load amps. So for a feeder feeding a group of motors, the largest motor's FLA is multiplied by 250, and then the FLAs of the remaining motors is added to this overall FLA of the feeder. So much like when we did the minimum circuit ampacity, we just multiply this factor times the largest motor and then just the flat value of the other motor's FLA. Remember that this is in conjunction with the minimum wire size determined using the MCA. So while this is the maximum value allowed by the NEC, it is not the typical value used in good electrical design, at least for a single motor. Using these defined terms and guidance of the NEC, we will now look at the steps required to size a branch circuit for a motor. The first step is to gather the proper information about the motor. The critical information that we must have to do this are first, is it single phase or 3-phase, which whoever is supplying the motor should be able to tell us this. What's the voltage of the motor? And then what's the horsepower of the motor? So these 3 things are critical. And we should be able to get these from the supplier or from a cut sheet or from something. We should be able to find this information. Additional information that we might be able to, or might be given to us, is the full load amps or running load amps. that might be given to us, but not always. And the maximum overcurrent protection, this might be given as well. So we'll always should be we always should have the first three items. We might have the fourth and fifth. When we more often have these than not is if it's a package unit or an assembly or a skid. You might hear these different things called, and these would be things like the HVAC. If they have an air handler, many times it'll have 2 or 3 motors on it, but it's just a single point that we connect to. So when they do that, they sometimes do the calculations for us and say, hey, the full load amps of this unit is this, and then the maximum overcurrent protection for this unit is this, while there might actually be several motors in there. Again, but 4 and 5 are many times not given. So even in those package unit situations, we may not have that, and we have to do it ourselves. But more often than not, if it's a package unit, we have 4 and 5. So now we're assuming we have all of these values. So we can now use this information to look up the value for the full load amps for the motor per table for the NEC tables. Once we have this value, we then multiply that by 125% to give us the MCA, or maximum circuit ampacity. We now use the maximum circuit ampacity along with the appropriate table from the NEC, which is almost always 310.15, to determine what the minimum size wire is required to feed the motor. Now that we have our wire size, we now must determine what size breaker to feed the motor with. As mentioned before, motors are a very special case as they typically have a very high initial inrush current as the motor starts that settles to a much lower steady state value once it is up and running. To accommodate this, the National Electrical Code allows us to significantly oversize the breaker feeding the motor to allow for this inrush current, but there are limits to this. Breakers feeding motors are allowed to be oversized by a range of factors that are governed by the NEC table 430.52, and we'll look at that on the next slide. So here's table 430.52. Again, this is the maximum rating or setting of motor branch circuit, short circuit, and ground fault protective devices. And you'll notice they have different types of motors here. So you have single phase motor, you have AC polyphase, other than wound rotor, squirrel cage, design B, energy efficient, synchronous, wound rotor, direct current. So there's several different types. And then you also have different types of protection. You have non-time delay fuse, dual element time delay fuse, instantaneous trip, inverse time breaker. So for most of the cases that we will deal with, we're going to live over in this right hand column. So this is the inverse time breaker. So remember, this is our thermal element. And so with this, you can see we stay pretty much in the AC polyphase motors. And so that's going to be the 250%. So either single phase or one of those guys. So the maximum we can size our breaker is 250% times the full load amps. So that's where we will live. We might have occasions where we use this column, or we have just instantaneous trip only. Remember, we talked about this in the breaker lecture section. And so those are the breakers that use only the electromagnetic solenoid. So they just, as soon as they see a set value, they instantly trip, right? So whereas these guys, you have to see a certain amount of current for a certain amount of time. The higher the current, the shorter the time they'll allow. So that's why this one's choked down to 250. This one is just instantaneous. So we'll allow this one to go up to 800%. So if you have a motor that you know is going to be started under load a lot, like an industrial application or something like that, you might choose to put an instantaneous trip breaker on there and size this thing up, as high as you can to 800 amps. The other column that you might use on occasion is the dual element. So this is if, say for instance, you're tapping off, like we said before, we run one feeder that's going to be tapped off of to run several motors. Well, when we tap off, we might use a fuse disconnect. So if we use a fuse disconnect, then we would use this to size the fuses. And so in this case, the maximum that the fuses could be sized is 175% of the full load amps. And usually the reason for that is, as it says up here, those fuses are time delay, much like the inverse time breakers. So they're going to need to see a pretty high current for at least some defined period of time before they trip. So we don't usually size those quite as high. So you can see from this table that there are several different types of overcurrent protection that can be used here, and the factor range varies depending on what is used. So for most applications, thermal magnetic breakers are used so that the two columns to the right apply to these types of breakers. When this is the case, the lower of the two factors should be used, which would be the far right column. So this gives us a range up to 250% for our breaker. For most applications, though, the rule of thumb is that we use around 175% under normal circumstances. So, breakers that would be feeding, mechanical equipment or some other equipment like that, if we're using the inverse time breakers, which we almost always are, then we usually size those to 175% under normal circumstances. But that's not always the case. This can vary, though, depending on the use of the motor and if it's expected to start under full load. If it is, then we would upsize this breaker size, like for an elevator or something like that. We might use something larger. So now that we've gone through the steps that we need to take, let's look at an example of sizing a motor circuit. So we want to apply these steps, and so assume we're asked to supply a motor with the following characteristics. Number one, they tell us that it's a three-phase motor. Number two, they tell us that it's 208 volts. And number three, it's a 15 horsepower motor. So this is the minimum information that we need to do this, so we should be able to accomplish this for this motor. So we will now take these values and refer to table 430.250. Remember, 430.250 is for three-phase, 430.248 is for single-phase, so 250 is the one we need to determine the full load amps for this motor, and that's what we're going to use to start our calculations. So here is the table for three-phase motors, full load current, and so again, we verify we're on the three-phase table, so this is the right one. Remember, we don't come over to this side. We stay out of the synchronous motor area unless you have specific instructions to go over there. And so we know the voltage is 208, so we'll know we'll be in that column there. And the horsepower was 15, so since we have all this laid out for us, then we just extend the two arrows here. And there we see that our full load amps should be 46.2 amps. So for a 15 horse 208, the full load amps is 46.2 amps. So this is our starting point. So again, we'll write that down. FLA is equal to 46.2, and now we're ready for the next step. So the next step is to determine the minimum circuit ampacity. So we remember that to find the MCA, we multiply the FLA by 125%. So here's where we do that. So FLA 46.2 times 1.25 gives us 57.75 amps. So this is the amount of current that we use to size our wire now. So this is the value that we use in conjunction with table 310.15 to obtain our wire size, and we'll see how to do that. So here's our table 310.15. So we also need to know what type of wire we're using. So we assume we'll be using the 75-degree column, THHN, THWN, so we'll be on the THWN side. So that would be this column here. And then we need to locate go down that column until we find the number of the MCA or the next higher number. So when we extend that down, 65 is the next higher number. So then we read over to the left to give us our wire size, which we do here. And we see that we're going to need at least a number 6 wire run to this motor. So again, from this table, we see at the minimum conductor size that we need is number 6. Remember, we can go larger, we just can't go smaller than that. So now that we have the conductor size, we need to determine the maximum overcurrent protection to feed our motor. To do this, we need to know what we are protecting the motor with. So we should always assume we're using a thermal magnetic breaker unless told otherwise. So making this assumption, we now use the NEC table 430.52, which we looked at earlier, to determine our multiplication factor as follows. So here's 430.52. Again, we're going to stay in the inverse time We're an AC polyphase motor. So we come across, and so our maximum is 250, so 250% of the full load amps, not the MCA, but the FLA. So from this table, we see that we can oversize this breaker by as much as 250%, but we're going to assume normal use unless we're told otherwise. So we remember the rule of thumb then is about 175%, so let's use that. So that being the case, we're going to say that our MOCP is going to be our full load amps times 175%, so that's 46.2 times 1.75. That gives us 80.85 amps. So this is our maximum overcurrent protection. However, we have to use standard size breakers. So there are two standard sizes of 80 amps and 90 amps that are close to this value. So which one do we use? Well, that's a good question. So for the NEC says that for a motor, a single motor, we can round up to the next standard size. So in this case, we would use the 90 amp breaker. Even if we do that, we're still well with under the 250%. So this shouldn't be too much of a surprise. And we'd rather have the breaker higher than lower because, last thing we want is some nuisance tripping. So if we choke the breaker down too low, our motor may start under some load. If it does, that would cause that inrush current to go higher, and it might trip our breaker if we have it set marginally low. So we'd rather go a little higher than lower to keep that from happening. So we now see that for a three-phase 208 volt 15 horsepower motor, we'll need to feed it with the following. We'll need 3 number 6 phase conductors because it's a 3-phase motor. And we'll have that protected by a 90 amp circuit breaker. So are we done? Of course not. That's only the wire and the breaker size. We still have conduit and ground wires and stuff like that, which we haven't sized for any of our different branch circuits. All we've sized so far are breakers and phase conductors. So the next couple of lectures we'll look at how to do that, because conduit sizing and ground sizing is going to be the same no matter what type of branch circuit you're feeding. So again, we still have to size the conduit that we're going to use. Plus, then you still have to size the ground wire, just like I said, to run the motor or to protect the motor. So these two tasks are the same, again, regardless of the load that we're dealing with. So we will look at that in the next couple of lectures.